Happy Trade Center, we are live.
Don't ask me. So, section 10.1, we want to talk about three things: temperature, thermal energy, and heat. And all three of them are actually different ideas or different things. Late human. So, temperature, energy, and heat. First of all, here is our vocabulary word for the day. And I need to do this, because by default it does that, which drives me crazy. And then I can do this, and yay, I got my pens back. Kinetic, molecular, theory, or KMT, which I'm going to use from now on, please, for short. Kinetic molecular theory explains that all matter is made up of tiny particles. That's the molecular word in the KMT. The word kinetic in English means moving. So these particles, both atoms, and when atoms combine together, we call them molecules. So these particles are constantly in motion on the subatomic, on the atomic, on the microscopic scale. They're moving. And kinetic energy is the energy due to motion. So when we say kinetic molecular theory, what we're saying is all matter is made up of particles, atoms, and molecules, and kinetic, they're all vibrating, they're moving. However, the particles of a substance move differently for different states. There are three main states of matter: solid, liquid, and gas. There are more, by the way. There's, I think, 9. Plasma and some really obscure ones. But the three main ones, the ones that show up on the Earth all the time. You've all seen plasma, by the way. A flame is plasma. Solid, liquid, and gas. In which one do you think the atoms are vibrating the least? Solid. So I wrote down here in blank, particles vibrate slightly but don't change position. That's in a solid. And then I have two blanks. I have in blank, particles vibrate more and move around within a set volume. And then the next one says, in blank, particles vibrate greatly and move around to take all of the volume available. Which one of those do you think is liquid? Which one of those do you think is gas? Okay, liquid's the second one, because the liquid, it'll fill up a cup, but it won't overflow. If you put a lid on the cup, it won't suddenly go up and touch the lid. It'll just stay at whatever level. So it'll fill a volume, but it won't fill all of the available volume. Liquid. I guess I should say in solids and liquids. And in gases, particles vibrate greatly and they move around to take all of the volume available. So I found this picture here. It's supposed to show, well, starting from left to right, that's what a solid should look like, that's what a liquid should look like, and that's what a gas should look like. And if you want to see more, page 424 in your text has a few more lovely pictures, but you don't have to worry about it right now. Instead, you can choose to turn the page. We're going to give you 3 definitions today. The definitions are in the title of the lesson. We're going to define temperature, we're going to define thermal energy, and we're going to define heat. And I'll try and then talk about what burns you and why you got burned, because many of you have been burned in different ways. It's 3 main ways that you can absorb heat. So the first word, temperature. Mr. Dewitt, can I abbreviate it with temp for short? Yes, but we'll write it out once just so I know how it's spelled. Temperature is the average of the kinetic energy of particles in a substance. By the way, I got to be fussy here. It is the average but not necessarily everywhere has the same temperature. So the movement of particles is what we measure as temperature, but it's an average. Just like in a swimming pool, you got cold spots, and you got warm spots, depending on where the drains are, depending on where the inputs are. But the thermometer on the side of the pool, that's telling you the average temperature of the pool. Okay? We measure temperature in 3 ways. We measure temperature in degrees, but there are 3 different scales. There's degrees Fahrenheit, mostly used in the US still, like complete idiots. There's degrees Celsius. And what's the third one? What?
Kelvin.
What?
Kelvin.
What? I'm going to get tired of that. My first name is Kelvin, for those of you who haven't figured it out. It was great for about 5 years until about 4 years ago when Google changed their algorithm. When you Googled the word Kelvin, the first thing that came up was a website devoted to Lord Kelvin, who invented the Kelvin scale. And the first page that came up was huge, and it just said in 3 words, Kelvin is God. It was awesome. Then Google redid their algorithm, and that doesn't work anyway. Okay. There are 3 different ways we measure temperature. So first of all, Fahrenheit, which is a stupid scale. Water freezes at 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. Dumb numbers, tough to remember. Meh. Celsius is a much nicer scale for our daily life. Water freezes at a wonderful, easy number to remember. What temperature does water freeze at? 0. And what would be a nice number to pick for water to boil at? 100. Nice scale. The only problem is when you get colder. So the lowest you can get is negative 273 degrees Celsius. That is 0 degrees Kelvin, and it's called absolute zero. What is absolute zero? And bear with me, my pen just stopped working like I said it does occasionally. What is absolute zero? Anybody know? You've heard the term, I'm guessing.
It's the lowest point.
Okay, it's 0 degrees Kelvin. And this is when you get so cold that all the molecules and all the atoms completely stop vibrating. Dane, what did you say?
So it's like the coldest point something can become.
Until about a month and a half ago, we thought it was the coldest point that anything could become, which is why we called it absolute zero. But do you remember in my definition of temperature, I said that temperature is actually an average? I will in just a second. Do you remember in my definition of temperature, I said temperature was actually an average? That means, for example, if you measure the temperature in a pool, some parts of the pool are higher, some parts of the pool are colder. It was suspected that maybe that was also true when you measured something at absolute zero. Maybe that actually meant you were finding an average temperature, which meant that some parts were warmer, but some parts were colder. And only about 2 months ago did they actually prove and find and measure some stuff that's, holy smokes, colder than absolute zero. By the way, outer space, it's about 2 degrees Kelvin, about 2 degrees above absolute zero. That's the average temperature. The Earth and our solar system is a huge, glowing, fiery hot spot compared to the rest of outer space. Temperature. Next word. Thermal energy. Thermal energy. That's the total energy of all of the particles in a substance if you put it, sorry, I'm going to say if you put the phone away. You got me off the track. If you added up all of the thermal energy in a substance, we call all of the heat energy, all the total energy, we call that thermal energy. So here's my first question. Suppose you have a small cup of coffee and a large cup of coffee, but they're both at the same temperature. Which one has more thermal energy?
Large.
So I've heard small, I've heard large. Either convince me that you're right, or convince me that someone else is wrong. Give me an argument. The large has more water molecules. So temperature is how much energy, how the heat, the temperature of one water molecule. The amount of energy, though, if you got more water molecules, you got more energy to deal with. So which one has more thermal energy? A large. Why? More molecules. More molecules. This is why if you have those 2 cups of coffee and you drop the same size ice cube into each one of them, which one would end up at a colder temperature? The small cup of coffee with 1 ice cube or the large cup of coffee with 1 ice cube? The small. Why? It had less thermal energy to begin with, and it had to use some of that thermal energy to warm up the ice cube. The bigger cup of coffee had way more thermal energy, and because temperature is an average, it had to give up a smaller amount. It had more left over to stay warm. Suppose you had a small cup of hot tea and a large swimming pool of lukewarm water. First of all, which one has a higher temperature, the hot tea or the lukewarm water? Which one do you think has more thermal energy? The pool. Why?
More molecules.
In fact, you can drop an ice cube into a pool. Will that change the temperature of the swimming pool at all? Technically, probably if you go about 15 decimal places along somewhere, it probably does. 0.000001 degree. But it's got so much thermal energy, you can handle that no problem. Drop an ice cube into a cup of tea, that will dramatically change the temperature. So you understand the difference between what we're talking about, thermal energy versus temperature? Third word. Heat. Heat is the amount of thermal energy that transfers from an area of higher temperature to an area of lower temperature. And this is how heat always works. Heat always moves from an area of higher temperature to an area of lower temperature.
Wait a minute, Mr. Dewick. Like my refrigerator gets colder,
not warmer. Actually, no. What your refrigerator is doing, it's got an engine system in the back that's pulling heat out of it to a lower temperature, but that removes some of the thermal energy in your refrigerator, which makes the refrigerator get colder, but you've actually moved heat to an area of lower temperature in the back. This is why if you put your hand behind the refrigerator, you feel it's very warm back there. Turn the page. So how can we transfer heat? How can you burn yourself? Heat can be transferred in 3 ways: conduction, convection, and radiation. And I found this lovely picture which I think explains the 3 of them fairly well. We have a boiling pot of water. Yours is black and white. Sorry, we don't have a color photocopier. But conduction, that's when you touch 2 objects together. They conduct heat from the higher temperature object to the lower temperature object. That's probably how most of you burned yourself. You touched something hot. Okay? Well, let's look at these. Conduction. That's the transfer of heat by physical contact or by direct contact. Heat is transferred from a higher temperature or, if we want to bring out kinetic molecular theory, from a higher molecular kinetic energy from molecules that are vibrating faster, group of particles, to a lower temperature group of particles with lower kinetic energy that aren't vibrating as fast. So when you burned yourself, when you touched something, what really happened on a molecular level, Jake, was the vibrating motion of the hotter object that you touched. It passed some of that vibrating motion to, let's assume it was your hand, your skin, your fingers, and those started to vibrate and they gained temperature, and that tells your nerves, owie, owie, something's wrong, and your reflex pulls back before you burn yourself severely. So example, a cold spoon warms up when you place it in a hot cup of coffee. It's in direct contact with the coffee. The coffee has a higher temperature. It gives some of its thermal energy into the cold spoon. The cold spoon raises its temperature. It gains thermal energy. Since the spoon gained energy, that also means the coffee lost energy and cooled off a little. Some terms: thermal conductors, most metals, transfer heat easily. This is why your cookware is all made out of metals. That's why most of our cutlery is made out of metals. We use metals all over the place. They transfer heat very, very well. What's the opposite of a thermal conductor? Begins with the letter I. Insulator. A thermal insulator, like a thermos. Some very good insulators: wood, styrofoam. They transfer heat poorly. That's why we use styrofoam for disposable coffee cups. Although we're getting away from that for environmental reasons, we've found other biodegradable substances that are almost as good an insulator, so we go with that. Next page. So the first one we had was conduction. Second one is convection. Convection. This is the transfer of heat in fluids, liquids and gases. So fluids are substances where particles can flow freely. And convection is the movement of heat from hot to cold within a fluid, or the movement of hot liquid to an area of cold liquid, the movement of hotter gas to an area with colder gas. And now we're going to do a little bit of chemistry here. When we're talking about gases and liquids in particular, when they're hotter, they're less dense. So because there is a density difference, hot fluid, low density, moves to cold, high density. This is how convection currents form. This explains a lot of weather patterns. So all of your houses, most of your houses have what's called forced air heating. And the way it works is we force hot air out of one duct. Hot air rises. You've all heard that term. Really what we should say is because hot air is less dense, it tends to float to the top. Cold air tends to sink to the bottom, but as it's doing so, it's giving up its heat energy to all the cold air molecules that it's bumping into, and eventually it cools off, and now it's going to sink to the bottom. And on the other side of your room, you'll have a vent somewhere that sucks the air back in, filters it, pumps it ahead with a fan, runs it through your furnace to heat up the air again, and the whole process goes over again. How does that explain weather? Well, where is the hottest part of the Earth? Along the equator. Where are the coldest parts of the Earth? Both poles. And that's why you get this cyclic weather, hot air getting heated up in the equator, jet stream, all of this. Now, it's much more complicated, though, because the Earth isn't sitting still. The Earth is also rotating and has mountains and things that bump against the air and push against the air. So weather is far more complicated than what I've just said. It's complicated enough that we think it may be impossible to ever predict it. There was, in the 1940s and 50s, Jessica, we thought maybe we would be able to predict weather. Specifically, the U.S. was hoping, they thought, well, maybe if we build a weather station every mile all over the U.S., we can predict the weather years in advance, which would be hugely useful. If you knew 10 years from now there was going to be a drought, you could tell farmers 10 years from now, don't plant those crops. Or if you want to have your wedding outdoors 6 years from now, you could call up the weather service. They thought, they were hoping you could say, yeah, what's a sunny day in June? And they could say, 6 years from now, oh, June 17th will be sunny. But in the 1950s, a mathematician proved that weather is what we call chaotic, that you can never predict it, sadly. Turn the page. The third one, the one that we kind of take for granted, radiation. This is the transfer of radiant energy by waves. This is what all of you have felt when you put your hands near a campfire. Because is the campfire touching you? No. Is there a convection current? You're too far away. It's not an enclosed space. There's no convection current. What you're getting is infrared radiation. You're feeling it on your hands as heat. In fact, this is what all of you feel this weekend when you were out in the sun on the glorious sunny days that we have. When the sun is out and you feel it hitting you, what you're feeling is the sun's radiant energy. In fact, the sun sends out what's called electromagnetic radiation. There's your, oh, come on. Oh, my pen stopped again. Let's try it one more time. So electromagnetic radiation is what the sun sends out towards us. It's the entire electromagnetic spectrum, all the way from X-rays and gamma rays. And oh, I gave you a picture here. Radio waves, the sun sends out radio waves. In your microwave, you have microwaves. By the way, 10 to the negative 2, what that's saying is that microwaves are 10 to the negative 2 meters long. They're about a centimeter long. And the reason that you can have holes in your microwave door is the holes in your microwave door that you can look through are a ½ centimeter long. Microwaves can't fit through them. That's how you can look into your microwave. That's why all of your microwaves have that little grill thing on the front.
Oh, that's what it's for.
That's what it's for. Infrared waves, we can't see infrared waves. We feel them though. That's what most of you feel as heat from the sun. Then there's the visible spectrum, which is right in this range. Then beyond what we can see, there's ultraviolet, but we do experience ultraviolet. What do UV rays do to us? You've all learned this, I hope, for your own health. Okay, this is what gives you a tan or a sunburn. Too much UV exposure, because ultraviolet rays, they have enough energy to actually damage your DNA slightly, and they can cause skin cancer. So that's why you put on sunscreen. X-rays have so much energy they go right through you. But because your bones are a bit denser than your skin, your bones will leave a ghostly image if we put a photographic plate behind it. That's what X-rays do. But again, it can also damage your DNA, which is why we try and minimize the number of X-rays, which is why X-ray technicians always get behind the lead wall before you take your X-ray. Gamma rays, we talked about those in our radiation unit. They don't turn you into the Incredible Hulk, but this is what we think of when we talk about radioactive poisoning. This is what makes your skin and DNA and things go yucky. So most of the heat that we feel is generally called infrared radiation. Any of you have infrared night goggles? I'm the only one? I forgot to bring them. I will try and bring a set by. All they do is, all of you, all the objects in this room, everything is giving off some amount of heat, some amount of infrared radiation. Now, put your hands near the table. All of you right now, put your hands near your lab table. You can't feel heat coming from there. Try putting your hands near your skin. You might feel, depending on your body type, you might feel a tiny bit of heat coming from you. Maybe not, because it's the same temperature as your hands, and so you really need a temperature difference to spot it. But I'm assuming all of you at least once have been near a campfire, yes? Okay. Or when the stove is on, put your hand near the stove element. You're feeling the infrared heat coming off of the stove element as well. Oh, the Earth's interior, the Earth has thermal energy on the interior. It comes from its core, because when it was gaseous and forming, as the core slowly compressed under pressure, some heat was generated. But also a lot of the geothermal energy that makes magma and lava and hot springs and geysers, a lot of that is, there are radioactive elements in the Earth's core that are decaying. And when radioactive elements decay, among many other byproducts, some of it's heat. So we get most of our thermal energy from the sun, but Hannah, not all of it. Which begs the question, what would happen if the sun vanished? How long could we survive?